tests have been posted. I'll give you back some sort of sheet, at least then you know where you lost some points on. Next time I see you, either in class or in lab or whatever, say, yeah, I held it too. Like if you turned in it late, you lost some points for turning in late. One thing I thought was self-explanatory, but if it's a word problem, use your own words. I mean, it's one thing if it's like so short and concise that it's kind of hard to define it without like kind of copying someone, but it's another thing if it's word for word the exact same answer, exact same explanation. And so try to use your own, reword it at the very least. However, there was some like I have posted a video going through at least one version of the test video, and I talk about the answers for the other version. Some of them are not that different. Most of them are a very similar idea. A couple things that I just thought I should mention that caught a bunch of people. One, when you're doing molality and freezing point depression, you're looking at the number of cation-anion pairs. So it's not how ionic the forces are. If it's ionic at all, it's a pretty safe bet. So if there's 2 cations and 1 anion, that's going to have a Van Hoff of 3. So like calcium carbonate would have 2, but lithium sulfate, which is Li2SO4, would have 3. So depending on which test you had, the answer was whatever had a Van Hoff of 3. One test had 2 possibles. One of them, the other test had 1 possible. Another thing, when you're doing the table, the graph, the chart, check the units. The temperature was in Kelvin. So when I say 10 degrees C, that is actually 283 Kelvin. So that tripped up a few people. Probably what tripped up the most people is I mentioned this in the video, but the first problem, which was, why does dichloromethane have a lower boiling point than chloroform and why does dimethyl ether have a lower boiling point than dichloromethane and chloroform, but a greater water solubility? And what I was looking for should have mentioned everything has London dispersion forces, no matter what. Everything has a dipole-dipole, but the strength of the dipole-dipole depends on the dipole moment. So you should have seen dichloromethane has a greater dipole-dipole than both dimethyl ether and chloroform. So it should have a stronger dipole-dipole. So that explains why it has a high boiling point than dichloromethane, but not this water solubility. So the water solubility is brought up on, you had to really think about this. No one really got this. That in water, what do you have? You have OH bonds. Water has hydrogen bonding. What do you need for a hydrogen bond? You need an OH and an O. Now, by itself, dichloromethane only has an O. There's no OH. But with water, it can make hydrogen bonds. And so in water, it hydrogen bonds to the water, and thus you get greater interaction and greater solubility. Even though dichloromethane has greater dipole-dipole, the hydrogen bonding makes the water solubility better. Now, the second part of that, where you compare dichloromethane and chloroform, well, dichloromethane has a greater dipole-dipole, so it should have a greater boiling point. However, London dispersion forces depends on the size. as you add more chloroforms, you're going to add more, as you add more chlorines, you're going to add more London dispersion forces, and so it increases the boiling point. The dipole by itself is not enough to the whole thing for the boiling point. So adding another chloroform, another chlorine, increases the boiling point. And one last thing on the last one as well, what I wanted you to do is, since it's 95 ethanol and 5 water, water is no longer the solvent. Ethanol is the solvent. And you had to say, well, ethanol, 95 mils of ethanol is about 75 grams. And you figured out 5 mils of water, how many moles of water? You divide that by 0.075 kilograms. And you get like the freezing point is something like -121. But that's neither here nor there. That was the test. It's curved at 15 points up. So it is what it is right now. We'll see what we're going to do for the next test, but that's a little ways away. In the meantime, we'll go ahead and start chapter 15. So, chapter 14 was all about kinetics, all about reaction speed. Chapter 15 is all about a new concept called chemical equilibrium. We've seen this a bit. We've heard the term equilibrium before, but we maybe not quite got a full picture of what this actually is. Now, kinetic, as I said, kinetics studies how fast a reaction goes, but kinetics will not necessarily tell you how far a reaction will proceed. It's all well and good to be a fast reaction, but a fast reaction means nothing if you get really low yield. So, some reactions will not go to completion. Some may not even get to 50% product, and that has to do with equilibrium. Equilibrium is essentially controls the ratio of products over reactants. The full scope of equilibrium is basically that in most reactions, when we drew that reaction diagram, that curve that went up and then over the hill and back down, you notice that there was no unbroken line. At any point, you could push the rock back up the hill. However, most times that is unwieldy. It's too hard to push it back up the hill as opposed to push it down the hill. Usually there is a small, it's like too energy intensive to put it back. But the idea is almost every reaction is reversible. Almost every reaction can be put back to its original place, given the right conditions. Now, in a reversible reaction, there is a forward reaction rate and a reverse reaction rate. So there's a speed to go forward and a speed to go backwards. Remember, the speed to go forward will have to do with the constant and the number of reactants. Now, because there's a speed to go backwards, it'll be the constant times the number of products. And there's going to be a certain point where the speed of the forward reaction will equal the speed of the reverse reaction. That essentially the forward reaction starts fast, and as the reaction proceeds, it slows down till it levels off. And the reverse reaction will start at almost none because there's no products, and it'll start up until it levels off. And the idea of equilibrium is the point when there is no net change in products or reactants. The reaction never stops. But there is no net change. For every product formed, another product is consumed to go back to reactants. So the net change is essentially zero. We lost one, we gained one. We gained one, we lost one. And so the reaction essentially seems to have stopped. However, you put in an influx of reactants, reaction picks back up again. You put in an influx of extra products, the reverse reaction will kick back in. So we have a situation. It's not fully stopped, but it looks like it's stopped to the outside observer. So just looking at this simple idea, N2O4, which is a colorless gas, will naturally break down into NO2 gas in two molecules. It's brown. So you can tell this goes based on a colorless gas darkens, essentially. As I said, the forward reaction for this elementary reaction is just K1, N2O4, the molecule naturally snaps apart. The reverse reaction for this elementary reaction is the two NO2 molecules bump into each other and stick together and form N2O4. So we have the forward reaction and the reverse reaction. If we looked at the reaction rate and the molarity versus time, you would see N2O4 starts high, goes low, levels off, doesn't seem to change. NO2 starts really low, builds its way up, levels off, doesn't change. Note, none of these go to zero. They just go to a point where they stop change, where the concentration doesn't change. Now, if we looked at the reaction rate versus time, the change in concentration versus change in time, you would see the rate of the forward reaction would start high, go low, go middle and level off. And the rate of the reverse reaction would start low and go high and level off, and they would meet at the same point. They would get to the speed forward equals the speed reverse. At the point where the two rates are equal, this is said to be at equilibrium. So note, equilibrium does not mean 50% product and 50% reactant. Each equilibrium is dependent on the chemical system because each system is dependent on its speed. So a different reaction rate would mean a different speed, which would mean a different equilibrium. So it's a case-by-case basis where we have to look at. But essentially, equilibrium is a known value that can be calculated based on reaction rates. But that's as far as we're going to look. We're not going to worry about reaction rates for this chapter. Reaction rates will just help us in the definition of this. But for the most part, we do not need to look at the actual speed to get to an equilibrium. Now, if equilibrium is rate forward, rate reverse, we can set those two situations equal to each other. And if we separate the variables, the constants from the concentrations, we get NO2 squared over N2O4 equals a constant over a second constant. Incorporating those two constants together, we get what's called the equilibrium constant K. So capital K will differ from our little k's that we used last chapter. The little k's were a reaction rate. The big K is all about looking at the ratio of the products to the reactants. The ratio of the products to the reactants. K is what's called a state function, which is, once again, one of those really weird things. One of those things we looked at when we saw capital H in enthalpy. A state function is independent of the mechanism. So speed or kinetics was highly dependent on the mechanism. This mechanism versus that mechanism meant this went faster, this went slower. We looked at the rate law was entirely dependent on the mechanism. The thing about equilibrium constant, it doesn't matter how many steps are between N2O4 and NO2. It only depends on the final product and the final reactant. Only depends on those two things, which will make K a little bit easier to calculate. In fact, K only changes, the only way to change a K is to change the temperature. K is otherwise entirely independent of all other variables. So if you want more NO2 than you got, and you don't want to increase the N2O4, you have to either heat it up or cool it down, depending on what we'll learn as the enthalpy of this reaction. Now, a reaction will always strive to approach equilibrium. Regardless of whether that means more products or more reactants, we'll always try to get to equilibrium. Now, while this only applies to reversible reactions, all reactions are reversible. All reactions are reversible to some extent. Even ones that go to near 100% completion are reversible. The only thing of it is that means the K is really, really, really product favored. It doesn't want to go backwards because the reverse rate would be essentially really, 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 really small. Really, really, really small, such that it doesn't seem to go backwards. It only barely goes backwards, if at all. But basically, for a given reaction, for any reaction where a reactant A and reactant B goes to product C and product D, we can write an equilibrium expression for that. That K, our magic equilibrium constant, is products raised to their exponents, raised to their coefficients, over reactants raised to their coefficients. Always products over reactants. The concentration of products over the concentration of reactants. This is what it means. It doesn't matter if the elementary reaction is this or that. We are only looking at the overall reaction of how many reactants get formed, how many products get consumed, because that's going to control where the equilibrium lies. Now, since concentrations are used, the compounds are only going to be expressed as either molarity or pressure in atmosphere. Here's one of the harder bits that often trips people up. Solids and liquids are not considered in an equilibrium expression. They do not have a concentration capable of changing, so they are independent. If I put, for example, zinc plus, let's write a reaction, like go to the doc cam and write a reaction real quick. Zinc solid plus HCl aqueous goes to H2 gas and zinc chloride aqueous. This pure zinc, pure elemental zinc, will not affect the reaction rate, will not affect the coefficient. It is incapable of having a concentration of changing. It is independent of the concentration. So our K expression would have to do with products, H2, or zinc chloride over our HCl. So I have to balance that. So 2 HCl, so HCl squared. So writing the K expression, pure solids, pure liquids are going to be entirely ignored. We only want to look at concentrations capable of changing, because How are you going to measure the change in concentration of a pure solid or the pure solid? If it's dissolved in something, then it becomes a concentration that you can deal with. But if it's a pure solid being mixed together, we can't quite measure how does that change. Nope. Now, the first thing we can do with K is just look at it on a just sheer magnitude scale. If K is always products over reactants, products as the numerator, reactants over the denominator, you can tell something about a reaction depending on the relative size of the K. If K is very, very small, meaning it's much, much less than 1, it means the reaction really doesn't like to go. If I start with 50 reactants, 0 products, maybe by the end I only have 48 reactants and 2 products. It means that the denominator is really big compared to the numerator, which is really small. It means the equilibrium will lie to the left. More reactants will exist than products. The reaction will not occur very much, if at all. If K is very large, meaning much, much greater than 1, it means the equilibrium lies far to the right. It means if I start with 50 products and 50 reactants and 0 products, maybe by the end I have 1 reactant and 49 products. We've completely converted from reactants to products. We would have very high yield. So looking at whether K is very big or very small tells us whether this has shifted to the right or the left, whether the reaction goes to near completion or very low level of completion. Now, we can look at both 2 types of Ks, a Kc, which deals with concentration, or a Kp that deals with pressure. These are not quite the same things because pressure and concentration are slightly different units, but they are interrelated. Kp is very useful for looking at the equilibriums of gases. Kc is the one we'll use 9 times out of 10 because that will deal with all of our aqueous situations. But in order to convert between the two, we will go back to our friend, the ideal gas. Ideal gas law says PV equals nRT. Well, what is molarity but just N over V? N over V is molarity, moles over volume. So in order to get from moles over volume to pressure, we have to multiply by R and T. So if we have pressure and we're going to molarity, we would divide by R over T. And if we have molarity and go into pressure, we multiply by R over T. So the generalized conversion is Kp equals Kc times RT over the delta N. So what is that delta N? The delta N is the overall moles of products over reactants because each side would be times RT for every time you convert it. In this case, there is 2 products and 1 reactant. So we have R over T divided by R over T, RT. So the net effect is 1 over RT because the top half has 2, the bottom half has 1. In this case, since there's 2 moles of gaseous product, 1 mole of gaseous reactant would have a change in positive 1. But essentially, we're just doing it to both sides for as many molecules as we have. Let's, before we do that, I'm going to show another example. Like, let's go back to the doc cam. because we're going to get to this example a little bit later. But just a quick conversion. If I'm doing N2 plus 3H2 goes to 2NH3. That's a gas, that's a gas, that's a gas. And I want to go, what is Kp from Kc? Well, it's Kc times RT over the change in moles. Well, how many moles do we have on the right? We have 1, 2. How many moles do we have on the left? 1, 2, 3, 4. So the net effect is 2 minus 4, or -2. So you'd have Kc times RT over -2. If I set that up as a K, we'd have NH3 squared times RT squared over N2 times RT times H2 cubed times RT cubed. Working at that, RT squared cancels with 2 out of the 3 of RT cubed. RT times RT becomes RT squared. So if this altogether makes up our Kc, we're saying Kc times 1 over RT squared. So it's just a quick conversion between the two. Will we have to do that very often? No. But it is something that gets asked on occasion, because you're just using your mental capacity to convert between the two. Should be something that's done. Now, when it comes to actually determining this in lab, determining this on homework, we can treat this in 3 ways. If we know the concentrations at equilibrium, we can directly find Kc. If we set a reaction up, let it go, measure all the products and reactants, once I've given it a day or so, we've let it go till it finished. If we do that and we measure the products and reactants, we can calculate our K. Easy as that. That's one thing we'll be able to do. If we know our K, we will be able to find one of our concentrations if we know the other. So I measure one of them, and I know what K should be. I can find the other. And the hardest thing we will do, which was later, is solve both equilibrium concentrations for Kc if we know our initial starting point and we know approximately where it should end. Now, this is kind of weird, and we're going to kind of do this, but this will be very useful next chapter when we get to acids and bases. So this is something we got to work at in a simplified context before we can get to a more complex context. So looking at the first way first, if we have the equilibrium concentration of N2O4 is 0.5, and the equilibrium concentration of NO2 is 0.325 molar, what is K? So we're going to set up 0.325 squared over 0.5 to the first. We would get 0.211. This is neither extremely big nor extremely small, so it doesn't tell us that much about it, but it does say it's a middling reaction. We're going to have some amount of products, some amount of reactants. Now, here's a weird thing about K. Now, in kinetics, we cared very much about the units of our little k's. Our little k's always had to cancel out my concentrations to give us rate over time. Well, our big K will never have to worry about that. We're never going to have to worry that molarity squared over molarity should technically be molarity. Big K will never have units. We will never have to worry about how many atmospheres we have or whatever. We don't ever have to cancel units. If you get into physical chemistry, which is, God, like a junior level, senior level class, we'll talk briefly about that. But for you guys, it never has units. We're not going to worry about it. There's a systematic setup that we do that takes care of the units for us. But rather than overly complicate this, it just never has units. Now, if we have our Kc 0.211, we can find any concentration with the reactant or product. If with this Kc, because remember, Kc does not change unless you heat up or cool down this reaction. The only way to change that is to heat up or cool down. So once we know that Kc, we know if I have 1 molar N2O4 at equilibrium, how much NO2 must we have? If we have 0.34 molar N2O4 at equilibrium, how much NO2 must we have? So I'm going to set up that equation. 0.211 equals x squared over 1. So what do? I do 0.211 times 1, and then I square root both sides. Say if I increase the concentration to 1, I would get 0.459 molar products. If I decrease the concentration to 0.34, 0.211 times 0.34, we square root both sides, we get 0.268. That should fit nicely with what we had on the last one. If I have half a molar, it's 0.325. If I have 1 molar, it goes a little bit higher than 0.325. If I have less than a half a molar, it goes lower than 0.325. Less reactants means less products. More reactants means more products. So if I want more NO2, I'm going to need more reactants to start with. Now, so here's where we first try some math of our own. The N2H3, N2 plus 3H2 goes to 2NH3. So the first thing I say is, first, let us find our K and then utilize that in all the other problems. 5, 2, 6. I'm just writing this down so I don't have to keep on switching back once I get to the doc cam. 0.860. We get X, and we got 0.589. And then 0.475, 0.856. Okay. Copy down my little table. Go to the doc cam. Our K expression will not change the entire thing. So send this up. Kc equals products, concentration of NH3 squared, reactants, N2 to the first, H2 to the third. So that first situation, we know everything. So I'm going to plug in everything. So 0.406 squared, 0.5 times 0.7 cubed. Just a matter of plugging that in. 0.406 squared divided by 0.5 divided by 0.7 root 3, or to the third power. Please note, if you're going to do these two together, put them in parentheses. If you're going to multiply 0.5 by 0.7, make sure to put those in parentheses. You should get 0.961. So I could punch this in as 0.406 squared divided by 0.5 times 0.7 root 3. I can also do it like that. I got to make sure. Oh, what the hell? Oh, I see. 0.961. Whatever you do, don't do 0.406 squared divided by 0.5 times 0.7 root 3. Because then you're going to get a completely different number. You got to make sure order of operations is always in effect. Just because we write it like this doesn't mean you type it exactly like this in your calculator. We want to maybe type it like that into our calculator to avoid confusion. But okay, so we have 0.961. So we have our K, 0.961. The beauty of this is this K is going to be the K of all our reactions. So with that in mind, 0.961 equals x squared over 0.526 times 0.245 cubed. So the first thing we do is we isolate the variable. 0.961 times 0.526 times 0.245 root 3, or power 3. And that gives us 0.0074337 equals x squared. I'm going to square root both sides, and that's going to give us x. Now you can either square root or raise it to the half power, which is the same as a square root. So my correct answer is 0.0862. 0.0862. Okay. Now doing it again. Now we have to solve for a different x. 0.961 equals 0.589 squared over 0.860 times x cubed. To get x by itself, we can get the x over there and 9.61 over here. So we can say that rearranging the equation, x cubed equals 0.589 squared 860 times 9.961. 589 squared divided by 0.860 divided by 0.961. You get x cubed is equal to 0.41977. Now to get the third root, my calculator has a root power x, but you can also root to the power of 1/3. Also works. So I'm going to have 3 root answer to get x equals 0.749. So root 3 gives us our answer. Last one. 0.961 equals 0.856 squared over x times 475. 475 cubed. Once again, get the x by itself. You get x equals 0.856 squared over 0.961 times 475 cubed. But this one, fortunately, we just have to plug our values in. We don't have to square root anything. We don't have to do anything beyond that. So the concentration of X I got was like 7.11. Now let's go back to the PowerPoint. Double check that. Oh, geez. That screwed up everything. Should have got. Oh, boy. Squared. Oh, geez, that's where it is. A little typo right there with the nitrogen. That should have read 0.05. Should have read 0.05. That changes that by a factor of 10, and that changes everything. Well, rather than go back through and worry about that, we can look at the results. Our numbers are no longer going to match here, but the work would have been the same. The work would have been the same. The steps would have been the same. Just the only difference is our numbers no longer will match up with here because of always double check. Always double check. See. Yeah, okay. Oh, that's cool. Okay, 0.749 times. Okay. Nope, that way. Okay, did it. Yep. So I can easily fix this by actually so 9.61 was off by a factor of 10 from 0.961. This one, I got 7.11 for that value. That's also off by that same factor of 10. So dividing by 10 would change 7.11 to 0.711. Well, this one is that we do that same thing, but 3 times. So if I divided by root, the cube root of 10, I'd go from 0.749 to 0.347. And if I multiply this by square root of, if I multiply our answer for this guy by the square root of 10, we get our 0.73, 273. So it is still fixable. It's just a pain. We're not going to worry about that right now. But okay, here's what it means to be a state function. State function. because of a state function, we don't care the path. We just care about what is the product, what is the reactants. Which means if I write this initial thing N2O4, NO2 as that's products over reactants. NO2 squared over N2O4 is 0.211. If I write the reverse reaction, what happens? Well, I'm still going to have products over reactants. Now, my previous reactant is now a product. My previous product is now a reactant. So what have I done? I've just flip-flopped my equation. To get the reverse reaction, I'm just going to take 1 divided by our previous K. Because it doesn't matter how we do it. We're just looking at products over reactants. So if it was 0.211 before, it's 4.74 the other way. If I were to write a reaction that is doubled, so instead of 1 N2O4 goes to 2 NO2, we have 2 N2O4 goes to 4 NO2. So we just have to the 4th power over N2O4 to the 2nd power. And it'd be essentially like K times K, or 0.211 squared. Equally, we can combine multiple Ks together. We can combine multiple Ks together. So looking at sulfuric acid, this is something we'll look at later, can break down in a 2-step process. First, it loses 1 acid on the H2SO4, goes to HSO4 and H+, and goes under a second reaction where HSO4, 1 minus, goes to SO4, 2 minus, and H+. The overall reaction would be H2SO4 goes to SO4, 2 minus, and 2H+. So the K for the overall reaction is H squared times SO4 over H2SO4. While looking at each individual step, the individual step H plus times HSO4 over H2SO4, and H plus times SO4 over HSO4. If you multiply those together, you have HSO4 on top, you have HSO4 on bottom. When you have a number divided by itself, that cancels out. When you have the number times itself, that's simply squaring it. So H plus times H plus is H plus squared. So by multiplying the first reaction by the second reaction, we get the overall reaction. So that's what it means when I say this is a state function. It doesn't matter how many steps you put in there, as long as you're looking at the overall reaction, you're going to get the equilibrium for all the steps combined. So it doesn't matter how we go about doing it, we will get all the steps combined. So let's practice this and not hopefully screw this up. K for the following reaction: CO2 plus H2O goes to H2CO3, aqueous. The K of this 1.7 times 10 to the negative third. So CO2 aqueous plus H2O liquid goes reversibly to H2CO3 aqueous. They're saying the K of the solubility of gas is 0.8317. So CO2 gas goes to CO2 aqueous. So if that's that K, what is the decomposition of carbonic acid to gaseous carbon dioxide? So we're looking for the following reaction. So this is one reaction. There's our second reaction. We're looking for this reaction. What is the K for carbonic acid, aqueous, breaking down into CO2, gas, and water? This is one you typically see when you mix what over time your carbonated soda will go flat because this reaction occurs. Carbonic acid will decompose into CO2 gas as it bubbles out of solution. What is the K for this situation? Well, the K equation is, so we have the K for the reverse reaction, and we have the K for this reverse reaction. So we're essentially setting this up. Our K is our CO2 gas over our H2CO3 aqueous. Well, how did we get there? Well, we have our CO2 over CO2 aqueous, and we have our H2CO3 aqueous over our CO2 aqueous, which will cancel out. So here's a little bit here. If this is for the forward reaction, then the reverse reaction would be 1 over 0.8317. And if this number is for the forward reaction, then the reverse reaction would be 1 over 1.7 times 10 to the negative third. And if I'm multiplying these two together to get this, so I'm multiplying those two K's, so 1 over 0.8317 times 1 over 1.7 times e negative 3. Three. I'm making sure the order of operations here. If I do this right, if I plug this in right, I should get something like 707. 707. Let's check. Okay. Those two together, 707. So what does that tell us about this reaction? Is this reaction product favored or reactant favored? Just based on this? Well, 707 is a significant amount over 1, not enormous, not in the thousands, not in the millions, but it's significantly over 1. So will this reaction occur? Yes. Is this reaction going to undo itself? No. It's going to be one of those ones that goes to products and largely stays there. Once your soda goes flat, you can't put the gas back in the bottle. It's going to go, and it's not going to go back. We don't have the equipment to make it go back. Just more practice of this. More practice. So, looking at writing this down. Down on the doc. So before we go to the doc cam, we want to know this reaction. 1/2 N2 plus 3/2 H2 plus HNO3 goes to ammonium nitrate. Ammonium nitrate. What would the possibility of this reaction occurring? So our N2 plus 3H2 goes to 2NH3, with a K of 6.9 times 6.93 10 to the fifth. And ammonium nitrate decomposes to nitric acid and ammonia at a rate of 2.36 times 10 to the 16th. So looking at that, so what two reactions would we have to use? Well, one, we have to flip that guy around. Two, we have to have that guy in a factor of 1/2 to this, -1 to that. So we get 1/2 N2 plus 3/2 H2 goes to 1 ammonia. And you get nitric acid plus ammonia goes to NH4NO3. When I combine these will cancel out. They give us the overall equation. So with this guy, if I double the coefficients, it's the same as raising it to the power of 2. So if I half the coefficients, it would be K, the square root of our K. If I reverse the reaction, it's the same as taking K to the -1st power. K to the -1st power. Because I'm taking 1 over K. So for this guy, I'm having the square root of 6.93 times 10 to the 5th times 1 over 2.36 e to the 16th. Already, logically, my brain should tell me this is not going to be a big number. This is probably going to be a small number. So, if I get a big number, I probably typed this in wrong. But just to make sure, I'm putting in parentheses where they need be. So I type in the first number square rooted divided by the whole second number in parentheses to make sure I didn't think, and I get 3.52 times 10 to the -14th. So is that a big number? Oh no, that's really small. So what does this tell us about this reaction? This reaction is not really going to happen. Not really. In fact, the reverse would probably be true. It's more likely to into the nitrogen gas, the hydrogen gas, the nitric acid than it is to solidify as a solid. This doesn't tell us anything about how fast this will take. It just only tells us that is this likely to happen? No. No, not at all. Not at all. Because this K is really, really, really small. I will go ahead and stop here. We'll call it a little bit early because I don't want to get into reaction quotient Q just yet. But the idea here, what we'll get to is how do you determine if a reaction is at equilibrium? How do you check just by looking at the values whether a reaction is equilibrium? So that's where we will get to. Okay, so looking at this. To review. So, some of the first problems. Setting up an equilibrium expression. So you just got to write that. One of the things to watch out for when you write this is to put brackets. If they're asking for concentration, so if they say Kc or Keq, put brackets around our things. Even if we're dealing with gases, put brackets if we're looking at equilibrium. If we're looking at if we're looking at concentration. So all this becomes is what, like bracket C squared times bracket D over bracket A and bracket B. But I want to pull up something like, okay, this one is the first one where we would not have something in the denominator. We only have something in the numerator because we do not consider pure liquids or pure gases. Now, we do not pure liquids or pure solids. So this would just simply bracket C root 2 times bracket B. All that is over 1, or you could just leave it without a denominator because A is a pure solid, B is a pure liquid. The only time you're going to have A and B would be if they are, like aqueous or a gas. And the only time you're going to have a pure liquid is when it says liquid. So equilibrium constant is this. So if we have this, this, and this, find K. So it doesn't matter how much we're dealing with, and the number, you're just raising it to its coefficients. So we have P4 of 0.75. We have H2 of 0.58. P4, pH3 of 0.25. This should not be hard. Set up my K expression. My K expression is P4 times H2 to the 6th all over pH3 to the 4th. Don't worry that is big powers. We can deal with it. 0.75, 0.58, 6th. And don't worry that this chapter may have some really small numbers. That is the nature of K. You can have really small numbers or really big numbers depending. So looking at that, I've set up my K expression. P4 times H squared to the 6th, pH3 to the 4th. So I'm going to say 0.75 times 0.58 to the 6th, so power 6, divided by 0.25 power 4. That gives me a number that is 7.3. 7.3 or 7.309. No. So just set it up. Just set it. Elementary. So this one's so this one, they give us pressures. Gives pressures. What is the value of the equilibrium constant at this temperature? So notice they ask for Kp. So because Kp is given and they give us pressures, we can just do the same thing just with those pressure numbers. I'm not even going to bother with doing that. It's just you're going to set up your K expression, just find your values, plug them in, evaluate. That is going to be a lot of this situation. Set up your K expression, define your values, plug them in, evaluate. Or isolate the variable, plug them in, and evaluate. Here's one that asks you about the size of K. When K is a very big number, it means we're going to have more B. When K is a very small number, we're going to have more A. So we'll do one of these. Oh, this one, they're turning KC into KP. We'll go ahead and do that real quick. If you're given KP, KP is 0.0814 at 223. 23 Kelvin, degrees C. So adding 273, that becomes like 496 Kelvin. And the rule is Kc times RT to the N equals Kp. So the net change is be -2. The net change would be -2. Going to the dot chem. So if we have Kp, to get Kc, it's whatever our Kp is times RT squared. Because to get from -2 to the other side makes it +2. So we need R, which is 0.08206, and T, which is 496. So it becomes 0.08206 times 496, all that squared, times our 0.0814, which was our Kp. So you get our Kc, which is 134.8. 134.8. Let's try that. For that. We'll finish with probably this one. Yeah, so there's a couple problems. There's probably not going to be too many of those. So this one, it's setting up a new equilibrium expression. It's kind of looking at a state function. So, and state function. So yeah, like 9 and 10 are values with the state function. We won't be able to do this one right yet. So you can do up through number 10 based on where we currently are in the notes. But that is where we'll stop. That's where we'll stop for sure. I just wanted to give you some more practice for the money. So say thank you for your attention. Be working on this because this is something that will need lots of practice. It's something that we're going to build on, especially over the next 3 chapters. This K is not going away. Kinetics is kind of a flash in the pan. We're looking at it for this chapter, and when we get to nuclear chemistry, we will look at first order reactions again. We will look at it in lab. So, but for the most part, K is here. Little k was just that chapter and that chapter only. Big K is going to be here to stay. Even when it's not a big topic, it's still going to be ever present when we look at thermodynamics. It's going to show up in each chapter, except for nuclear chemistry. It's going to show up at least once in each chapter. So we need to make sure we understand this and how to calculate it. So thank you for your time. Goodbye.